Greetings and welcome to Chapter 6, the Normal Distribution. In Lesson 6.1, we're going to concentrate on the standard normal distribution. Get to know the new terminology for this lesson. Click on each of the words, learn its definition and meaning. When you are ready, click Continue. The normal curve is the continuous distribution that looks like a bell. It's probably the one curve you've been acquainted with because they say grades are usually in a bell-shaped curve. You'll have few F's, a few A's, but you'll have a lot of the middle grades. So that's a normal curve. It looks like a bell shape. It is the most widely used of all the distribution, but it's also the most widely abused of the distribution. A lot can go wrong very quickly with the normal curve. It can also be applied incorrectly. We have two parameters. We have the mean and the standard deviation. So our notation will look like x tilde in with our parameters of mean and standard deviation, mu and sigma. Our shape itself is symmetric around the mean, and therefore it looks the same on each side of the mean. Where the changes, what makes it really different from one to another, is the change in standard deviation. If your standard deviation is small, you can expect your normal curve to be very tall and thin, very skinny. As your standard deviation grows, the curve will shorten and flatten out. It's still a curve, but it will be more flattened out and widespread because your standard deviation is more widely spread. In previous distributions, we did calculate the probability density function, f of x. In this case, we are not going to calculate f of x. You do not need to memorize this function. We're really not going to work with the function. We know it's a bell-shaped curve, and we're going to stick with that. So our f of x is very complex because you can see it's a complex shape, but we don't need to memorize this, and we really won't have you create the probability density function f of x. One of the most difficult things that we can do is try and compare two values, but come from different populations. So one of the populations, its mean might be 25, but its standard deviation is 3, while the other population might have the mean of 45 and a standard deviation for 2. Well, a 20 over in the first population isn't going to mean the same thing as a 20 to the second population because of the different means and standard deviations. One way to deal with this is to move all of your values over to what's called z-scores. Z-scores are just a standardized way of looking at measurements. And you've actually used these before. I'm going to give the same example as I did before, which are test scores. When you take two different tests that have two different amount of questions, and let's say one of your tests is 15 questions and the other is 50 questions, one's maybe a midterm, one's a regular test, and you miss 3 questions on each. Well, which test did you do better on? Well, if you just go by the number that you missed, then you did the same on each test. But they're not the same. A 3 when your question count is 15 is not the same as a 3 when your question count is 50. What we do in that situation is we just turn it over to a percentage, and then we compare the percentages. Z-scores are very similar to that. What we're going to be able to do is to calculate this probability of a score occurring within a normal distribution and compare those two scores, even though they're from different normal distributions. As you can see, the normal distributions can look very different from one another. The green one, the mean is -2 and the standard deviation is 2. For the blue one, the mean is 0 and the standard deviation is 1. For the red, the mean is 2 and the standard deviation is 1/2 or 0.5. So depending on the population, it's going to give you a different graph altogether. And to compare that, we're going to reform these graphs to where they are the standard normal form, meaning it doesn't matter what mean or standard deviation you start with, we're going to, I would say, transform what we're given over to the standard normal form with a mean of 0 and our standard deviation of 1. Let's look at what that would look like using our notation. So our x realm is the normal with our average being our mu and our standard deviation being sigma. That's going to translate to z values, which sit in the normal with 0 being our mean and 1 being our standard deviation. We can do this transfer or this translation from x's to z for any x value. The equation to be able to do that, we've seen before, but we're going to use it extensively now. Z equals x minus our mu over our standard deviation. That produces this distribution where our mean is now 0 and our standard deviation is 1. It's fitting it into this new distribution. It doesn't change our x. It doesn't change where we start from. It just transfers it over into a new location, if you want to think of it like that. Here's our standardized normal curve. The mean is 0 and standard deviations are 1, 2, 3. -1, -2, -3. Going forward, what we're going to have to do is translate x values to z scores. And then once we get the z scores, we can start comparing two values. To lay down some groundwork about x values and z scores, when you calculate your z score from your x value, if it is positive, it means that x is greater than your mean. When your z-score is negative, that means your x is less than mean. That's all that means. If it's positive, it's greater than your mean. If it's negative, it's less than your mean. And if it's 0, it is your mean. So let's suppose we have two normal distributions. Our first normal distribution has the mean of 5 and the standard deviation of 6. Our second normal distribution has a mean of 8 and a standard deviation of 3. Let's look at an example and figure out which x is relatively larger. In our first distribution, our x value is 17. In our second distribution, our x is 15. And if we just looked at our x values as they stand, of course, 17 is larger than 15, but relatively larger to their own distribution. And to do that, we need to calculate their z-scores for each one. For the value of x is 17, its z-score is going to be 17 minus its mean of 5, all divided by its standard deviation of 6. And we get 2.00. For 15, we're going to say 15 minus its mean of 8, all divided by 3, and therefore its z-score is 2.33. Looking at the z-scores, we can see 17 is 2 standard deviations away from the mean. 15 is 2.33 standard deviations away from its mean, and therefore 15 is relatively larger for its distribution. Now, let's see if these x values are relatively the same. In both distributions, we'll say x equals 4. If x equals 4 in the first one and x equals 4 in the second, doesn't that mean they're the same value? Well, no. Remember, we're dealing with different distributions, and therefore we have to translate that over to a z to be able to really compare it. So when x is 4 in the first distribution, it's going to be 4 minus the mean of 5, all divided by its standard deviation of 6. We get a negative 0.1667. When we calculate the second 4, in its distribution, we get a z of 4 minus its mean of 8 all over its standard deviation of 3, and we get a value of negative 1.3333. So the second 4 is further away from its mean than the first 4. So negative 1.333 is much larger of a distance from its mean than negative 0.1667. So are they relatively the same? No, they're not. I'm going to walk through a problem, more so run through a problem. You've already kind of dealt with this, but we're just going to run through the concepts very quickly. Here's our problem description. Some doctors believe that a person can lose 5 pounds on average in a month by reducing his or her fat intake and exercising consistently. Suppose weight loss has a normal distribution. Let X equal the amount of weight loss in pounds by a person in a month. We're going to use the standard deviation of 2 pounds. So our normal distribution right now is a mean of 5 and a standard deviation of 2. Let's suppose a person loses 10 pounds in a month. What's our z-score? Okay, well, we just got to throw it into our equation. So 10 is our x value minus our mean of 5, all divided by 2. So 10 minus 5 is 5, divided by 2 is 2.5. This z-score tells us that it is 2.5 standard deviations to the, it's positive, so it's going to be to the right of the mean. What was the mean? Well, the mean is 5. So we got to keep that in mind. It is to the right of 5, which makes sense because 10 is greater than the mean of 5 anyway. Suppose a person gains 3 pounds, which is a negative weight loss. Then what is our z-score? Well, our z is going to be our x value minus our mean, all divided by 2. So negative 3 minus 5 is negative 8, divided by 2 is negative 4. So it is 4 standard deviations to the left of the mean. It is not negative 4 standard deviations to the left. It is 4 standard deviations, but it is to the left of the mean. Negative lets us know that it's left. Positive lets us know that it's right. The value itself is the number of standard deviations away from the mean. Now let us suppose that the random variable x and y have normal distributions and the normal distributions are as given. Our first normal distribution for x has a mean of 5 and a standard deviation of 6. Our y distribution has a mean of 2 and a standard deviation of 1. Then let's calculate an x value of 17. Now x goes along with the distribution of x, so I'm only going to use the mean of 5 and the standard deviation of 6. 17 minus 5 is 12. Divided by 6 is 2, so it has a z-score of 2. Now if y equals 4, then what is z? Again, we're only going to use the distribution for y when it comes to y values. So 4 minus 2 is 2, divided by 1 is 2. Oh, so that value is also 2. What does this mean? That relative to their own distributions, they are the same distance from mean. They are both 2 standard deviations away from their respective means. The empirical rule is a nice way of looking at the normal curve and getting some information out of it without even doing a lot of math. It's just something I would say that you learn or memorize. The empirical rule states, within 1 standard deviation below and above the mean, 68% of your data will fall there. In other words, 0.68 probability lies within minus 1 standard deviation and plus 1 standard deviation, that range. It also states that within 2 standard deviations, 2 below and 2 above, 95% of your data fits. In other words, the probability that your data will be in that middle area with 2 standard deviations below and 2 standard deviations above is 0.95. We can even continue this empirical rule one more step, and within 3 standard deviations below and above 99.7% of your data will fall. So yes, the probability of your data falling within 3 standard deviations of the mean, both below and above, is 99.7% or 0.997. Now that we know a little bit about the empirical rule, let's actually use it to our benefit. Let's suppose X has a normal distribution, its mean is 50 and its standard deviation is 6. Between what values of X do we expect 68% of the values to lie? There's going to be a low value and a high value. So it's this range of values. To calculate this, I know my low value is 1 standard deviation below the mean. So our mean minus 1 standard deviation will give us our value. Let's actually use it to our benefit. Let's suppose X has a normal distribution, its mean is 50 and its standard deviation is 6. Between what values of X do we expect 68% of the values to lie? There's going to be a low value and a high value. So it's this range of values. To calculate this, I know my low value is 1 standard deviation below the mean. So our mean minus 1 standard deviation will give us our value. 50 is our mean, standard deviation is 6, so 50 minus 1 times 6 gives us 44. Our high value is going to be 1 standard deviation above the mean. So 50 plus 1 times our standard deviation of 6 equals 56. So we expect 68% of our values to lie between 44 and 56. Between what 2 values do we expect 95% of our data to lie? Again, we need a low value and a high value. And this time, 95% correlates to 2 standard deviations below and 2 standard deviations above the mean. So for our low value, it's going to be 50 minus 2 times 6, and that equals 38. Our high value is going to be 50 plus 2 standard deviations of 6, and that equals 62. So 95% of our values will lie between 38 and 62. Now let's continue using the empirical rule one more time, and let's figure out the values that lie between the values for the 99.7%. We have a low value, we have a high value. We know that 99.7% of our values should be 3 standard deviations below and 3 standard deviations above the mean. For our low value, that's 50 minus 3 times 6, in other words, 32. Our high value is 50 plus 3 times 6, which is 68. So 99.7% of our values will lie between 32 and 68 for this problem. Now let's do one more problem. From 1994 to 1995, the mean height of 15 to 18-year-old males in Chile was 172.36 centimeters, with a standard deviation of 6.34 centimeters. Let's let our X be the height of our 15 to 18-year-old males in 1994 to 1995. Oh, 1984 to 1985. Excuse me, I missed it by a decade. Then our X will be the normal distribution of our mean of 172.36 and our standard deviation of 6.34. About 68% of the values will lie between what 2 values? And what are your z-scores? Now you might think, oh my gosh, my z-scores, that's going to be another calculation. Oh, nay. No, it's not. We know that for 68% of our data, it lies within 1 standard deviation below and 1 standard deviation above the mean. And therefore, we can immediately state our z-scores are -1 because it's 1 standard deviation to the left and 1 standard deviation to right, so our z's are -1 and 1. We still have to calculate what our x values are, but we can immediately say what our z-scores are. Okay, so our x low value is going to be our mean minus 1 standard deviation. So 172.36 minus 1 times 6.34, and we get 166.02. Our high value is going to be 1 standard deviation above the mean. So take our mean plus 1 standard deviation, 172.32. 172.36 plus 1 times 6.34, and we get 178.70. Now, let's figure out about 95% of the values should lie between what two values? And we want to know what our z-scores are. Well, again, the z-score part is the easy part because knowing the empirical rule, 95% of my data lies 2 standard deviations below and 2 standard deviations above the mean. That means my z is -2 and 2. Now that we got that part of the way, let's deal with our actual values. Our low value is 2 standard deviations below, so that's going to be 172.36 minus 2 times 6.34. That equals 159.68. For our high value, that is 2 standard deviations above the mean. So the mean plus 2 standard deviations, 172.36 plus 2 times 6.34, that gives us 185.04. What about 99.7% of the values? What values should they lie between? And what of our z-scores? Well, again, empirical rule states that 99.7% of our values should lie within 3 standard deviations below and 3 standard deviations above the mean. So our z-scores, -3 and +3. Our x values, for our low, 172.36 minus 3 times our standard deviation of 6.34, giving us 153.34. Our high value is going to be plus 3 standard deviations. So 172.36 plus 3 times our 6.34, that gives us 191.38. You've reached the end of this lesson.